I want to start by just kind of the whole point of this particular discussion is, it could be very etherical about the concepts of energy, what is energy, where it comes from, and how it's useful. But there's also the pragmatics that a lot of physics is in the application. And when we talk about the application, we're talking about what can you do with this information and how is it useful. So we have solved a number of problems using Newton's laws. And on their own, Newton's laws can be challenging just in that there's a lot that you have to do, and it is technical and detail-oriented and detail-focused. But ultimately, if you are careful, you'll understand everything about a system. You'll be able to really anticipate the future of that system, and you'll be able to make grand predictions about what will happen to that system in the future. You could also probably use it to make decisions about how you might design something or make something. There's other applications of it, and work energy is an application. One of the things about the work energy theorem and work energy in general is that it's really good at dynamic situations in which things are moving. In fact, that's one of the pros, is that generally when you're dealing with work energy problems, they're very good at dealing with velocity. That's directly related to the fact that kinetic energy is 1/2 mv squared. So when you're changing something's energy, you are probably dealing with its velocity. It's also very good at dealing with position and displacement. Now, you might ask why I'm generating a pro-con list. It's not complicated. I'm not going to tell you on the test that this is a work energy problem. You have to figure that out and know whether you're supposed to be using Newton's laws to figure out a problem or whether you should be using work and energy to figure out a problem. So it's not going to say this is the work energy problem. But if you have a problem that's asking a lot about velocity or is asking a lot about displacement or gives you velocity or gives you displacement, very likely work energy is a good place to start. But there are cons. There's several things about work and energy that they're just not particularly good at. One of them is dealing with time. You won't see anything related to time, hardly at all, in any of the conversations we have. The work energy theorem and the definition of work, they don't ever have anything in them that's related to how long it might take for something to happen. So although we know that velocity tends to be pretty related to time, this won't tell you how long it takes to go someplace or how long it'll take to get up to that speed. Which brings you to an obvious, I hope obvious, another point that it also really has nothing to do with acceleration. You're not going to see it there. You're going to need to do something else with the information if you want to get acceleration or if you want to get time. Lastly, it's not particularly good at figuring out an individual force. And lastly, direction. Energy can't deal with direction because direction isn't a part of energy. It's all scalars. You may be able to infer the direction that something occurs or infer the direction that something is moving, but you're not going to be able to use energy to tell you the direction that something is moving. So when we look at what the pro side is versus the con side, energy is great at dealing with velocity and displacements. It's going to be fantastic for that. But it's not going to be particularly good at dealing with anything else related to our motion variables, and it's certainly not going to tell you direction. So I'm going to pick up from there. I'm going to go to the back of the room. We were talking about Q equals mc delta t. And I wanted to make the connection that Q is a form of energy transfer. We're looking at a broader idea today, and that's work. It could be said that Q and Q equals MC delta T is a method for changing something's energy. That it's a subset of how you might do work on a system where heat is of primary importance. But we're going to talk about a physical system, a system in which our objects aren't a collection of materials that we're studying in mass, but we're studying individual objects in general, or small systems that have individual objects in them. And therefore, we're going to define work based on what happens to an individual item or an individual object. Now, there's two ways to define it, but the most generalized definition is going to be an integral and a dot product, which is a lot to take in for those of you who are kind of new to vector mathematics, which I would assume is almost all of you. And worse, we're going to add an integral symbol, and that's new to a lot of you in the room too. So you have to understand what this is saying, and there's a lot of pieces to what it's saying. So I'm going to kind of continue with the trend I talked about yesterday and kind of do a kind of a map on this, or a thought diagram on this, so that we can kind of talk about what all these pieces are. And I want to start kind of at the end. This dx is another way of saying delta x, but for small increments. So this is saying that if you move an object a small amount or have a small displacement, so this is what it really is, just a small displacement. Okay, so if an object moves a small amount, and this is talking about the force that may or may not cause it, but the force associated with that movement. This type of multiplication isn't standard multiplication that you guys have done in the past. This is called the dot product, and the dot product is a way of multiplying two vectors together. There's several different ways of multiplying vectors together. It depends on what the purpose of that multiplication is to determine which product you would use. This product is specific to this kind of calculation where we want to know how much of the force is in the direction of motion. That's what this dot product is about. It's asking how much of the force is in the direction of motion. Now, this integral symbol is saying that you need to add up this product for the entire, well, add up. I want to add up this product for the entire displacement, I guess we say of the object. That's what all the pieces mean. Now, that doesn't tell you what work is, it's just telling you what the pieces of that equation mean. Now, that equation can be made a lot simpler if the force is constant. If the force is constant, then I don't have to write it like this. If the force is constant, I can write it in a much easier way. So let's take a look at what it would look like if it was constant, and then we'll come back to what this actual definition is. If the force is constant, then I don't have to worry about summing it up. I can just say, all right, take the force. Now, I'm writing the symbols a little different this time because I don't need to take the direction of the force into account this time. So I'm writing this as the magnitude of a vector. So these bars here are supposed to be that tell you that take just the size portion of the force. So although I know you guys probably consider those to be the absolute value, that's ultimately what it is. But in a vector, the absolute value is the length of the vector. Does that make sense to you guys? I mean, if it was just one dimensional, the number would be positive or negative, and that's all that matters is how big the number is. But this can be in any direction. And we're going to multiply this by the entire displacement. Again, this is just the magnitude of the displacement. Now, remember, we were dealing with the dot product before, and the dot product was supposed to be telling us how much of the force is in the direction of motion. That's quite literally just taking the cosine of the angle. And this is the angle between the force and the displacement. Now, this is only useful if the force is constant. It's the only time you can use it. So you have to know or judge when you're starting your problem if the force is going to be constant or not. If it is, you can use this one, and this one's pretty easy. If it's not, so you can't use it. I want to demonstrate it. I want to demonstrate it with one that's really, really, really easy. Okay, I want to start with something that you guys can do probably with little difficulty and apply it here. So we're going to take and just slide a box across the ground. Now you're going to have to use what you've already known so far this year to figure this out. So I want to predicate this that you're not going to be able to forget the things we've already done. So consider a box on a level surface that's experiencing a horizontal force of 20 newtons. Let's say it's a 5 kilogram block. Okay. And let's say that there's a coefficient of kinetic friction of 0.1. So let's say that due to the action of the force, the box moves a distance of 5 meters along the ground. Work is about an individual force. So I'd like to determine the work done by each force acting on the box. This should be pretty straightforward. Does everybody understand the question? Or at least, did you write the question down? So the work done by each force acting on the box. Now, before we even start the problem, how many forces are acting on the box? Well, there's at least one because it's drawn up there. Can you name another one? Gravity. So there's going to be a gravitational force acting on the box. There's going to be a frictional force acting on the box. And is that it? Normal force acting on the box. Seems to me that before we even start this problem, we should probably figure out the size of each of these forces. and you should know how to do that already. We passed this unit. So I'll give you 60 seconds, and I'm going to call on, well, two people. One to tell me the normal force and one to tell me the frictional force. Yeah, I'm not going to let you go, right? You know that. So I guess we'll have to spend a little time on it. Did you draw a free body diagram? All right. In your free body diagram, have you decided whether the net force is ma or 0? All right. So did you break this up into the x direction and the y direction? So N minus 50 newtons equals ma. So the reason I asked if you broke it up into the x and the y direction is you would have wanted to line up the x or y direction with the direction it accelerates. So do you think it accelerates up or down, or do you think it accelerates left to right? All right. So I'm thinking that if it accelerates left to right, then left to right is going to be my net force equals ma, and my up and down is going to be my net force equals 0. So I don't think I'm going to set N minus 50 equal to ma. So what should I set it equal to? 0. All right, so if I set it equal to 0, then what's the normal force likely going to equal? There it is. So the normal force equals 50 newtons. All right, so Juan, can you tell me the size of the frictional force? How'd you come to that conclusion? So you use friction equals mu times the normal force. We just found the normal force, so you found friction by multiplying together, and it's 5 newtons. Yeah, there we go. That's what had to be done. Not a whole lot here yet, but all we need is the size of the forces. Now, I think there's going to be some clear shortcuts in a few minutes, things that maybe we didn't have to do in this problem. But until we get to them, or until you see them, I'm not sure that we can apply a shortcut. If there are 4 forces acting on the object, then there are potentially 4 different forces doing work. All of these forces are constant, though. So work is going to equal the length of the force vector times the displacement of the object times the cosine of the angle between them. Let's start with the 20. What's the size of the 20 Newton force? The size of the 20 Newton force is 1? 20. Yeah, I think 20 would be a good one. What is the size of the displacement of the box? Alrighty. All right, here's a hard question, I guess. Maybe, not really. What's the angle between the 20 and the direction of the displacement? Okay, good. We're on the same page here. So cosine 0 degrees. There we go. All right. A little nervous about this next one because it was harder to get the normal equals 50 than I was anticipating. So what is the size of the normal force? 50. What is the displacement of the box? It's still 5 meters. The box still went 5 meters. Is that not true? Okay, 5 meters. What is the angle between the displacement and the normal force? 90 degrees, yeah. Now, look, was there ever a component of the normal force in the direction of the motion? I mean, if there never was, we probably didn't have to deal with the normal force, right? Is the normal force contributing to the motion of the box? Not in a direct way. There's an indirect relationship in that the normal force is creating friction. but it's not the normal force that's in the direction of motion. It has no component in the direction of motion, so it's not contributing to changing the energy of the box, not directly. What's the weight of the box? Guys, come on. It's 50. In a few minutes, I'm going to probably lose my patience a bit. But yes, the weight of the box is 50. How far does the box travel? What's the displacement of the box? Still 5 meters. Way to go. Now, what is the angle between the displacement and the weight? Still 90 degrees. We're talking about this angle here. Weight's downwards, displacement still to the right. I'm not asking hard questions. Okay. We have one more work to set up here. Juan, what was the size of the frictional force again? 5 newtons, thank you. And Kendall, what is the displacement of the box? Still 5 meters, excellent. Now here's the hard question. What is the angle between the displacement and the friction? 180. It is this angle. That is the angle between the displacement and the frictional force. This is what it takes to calculate work. It's not particularly challenging if the force is constant. The issue is that every single force could possibly be doing work if there's a component of that force in the direction of motion. Now, I don't see you writing that down, but some of you guys gave me some pretty interesting answers just now for what should have been simple roll call answers. So I'll say it again, only forces that are in the direction of motion can contribute to doing work on the object. Now, it is probably important to understand that any force that's within 0 to 90 degrees of the displacement is contributing positive work because the cosine of any angle between 0 and 90 is positive. That'd be a good thing to write down, I think. And any force that is acting at an angle between 90 and 180 is taking away energy. It's not contributing to add energy, it's trying to slow the object down. So those are probably doing negative work. I'm saying this because I thought you guys would kind of see that or maybe guess at that, but this class needs to be kind of hit over the head with the obvious. So any forces that are on this side of the direction of motion, they're going to be adding to the energy of the block. And any forces that are on this side of the direction of motion are going to be taking away from the direction of the block. Wow. All right. This part not too hard, but I have fear, so let's handle that fear a bit. 20 times 5. Well, do not reach for your calculator. Oh my, do not. 20 times 5 you can do. What is it? 100 joules. That's right. Do I have to bother to calculate the next two? No. Cosine of 90 is what? 0. So these are both 0. What's the work done by friction, though? It's negative 25 joules. As discussed yesterday, positive amounts of work increase an object's energy. Negative amounts of work take that energy away. So although you were pushing the box across the floor, perhaps, and you were giving the box energy, at the same time that you were giving the box energy, the floor was taking some of it away. Now, some of these forms of energy can be recovered, but some can't. In the case of friction, friction is what's considered a non-conservative force, meaning the box was being scraped along the ground, that energy, this negative 25 joules, was due to a non-conservative force, which means that energy just was wasted. It's gone. It just heated up the floor. It's difficult to recover that kind of energy. But this force was an applied force. We don't really know whether it was conservative or not. It doesn't matter. This was adding energy to the box. But at the same time, the floor was taking that energy away. What's the net work done on the box? The word net work is exactly the same kind of application as net force. Net work is the sum of all the work done on an object. I'll say it 3 times for those of you who need an extra cue to write things down. Net work is the sum of all the work that was done on an object. So this box had a total of 75 joules of work because the net work is the sum of all the work that was done on the object. Now, this part is kind of a big important little thing that you need to kind of get in there. We said that anytime we change the energy of an object, work has to be done. In this case, there's something called the work energy theorem. Which states that the net work done on a system is equal to the change in kinetic energy of the system. And the net work that's done on a system is equal to the change in kinetic energy of the system. I hate to do this, but if that work is positive, then can you see that the velocity of the object had to increase? It had to be going faster. And if that's negative, then the object has to be going slower. But there's another definition of net work. Net work is also equal to the work done by the net force. The net work is equal to the work done by the net force. So it could be written this way. Now, I know there's not many of you in here, but there's a few of you. We can do simple math, I think. Maybe. Need you to pay attention to this. Let me, instead of writing that as a dx, just write that as a delta. Just for right now. I don't want to make this harder than it has to be. It's already kind of hard. This is just the definition that I gave you for work, except that instead of having an F, you'll notice that we have the sum of the forces. That is the difference, because the sum of the forces means net force. So don't treat that arbitrarily and don't treat that as Newton's laws or something. That is saying net force. So if you add up all the forces acting on an object, that would be the net force. And deal with delta X gives you the change in kinetic energy. That also means that net force equals the change in energy divided by the change in position. And this is going to have implications later. And so I want to have introduced it now. that there's more than one way to figure out net force. You don't just have to add up all the forces. There's other ways to calculate net force, and this is one of them. I want you to try an example this time without my assistance, and I would work with your friends at the table. I'm not going to change this very much because I don't think I can. I think I'm going to stick with something relatively easy. So, and this is very much something that's like your first homework question. Do you think more or less work is going to be done on the box this way? Same size force, same displacement. Now, I hear less. It is reasonable to believe that there's less of that 20 Newton force in the direction of motion. So it's reasonable to believe that less work will be done. But what else is happening now that we've pitched that force upwards? What's that?
The direction of motion is only to the right now.
I don't think so, because I don't think that's enough upwards to lift the box. But there'd have to be at least 50 newtons of force upwards to get the box to be lifted off the surface. So I don't think the box will be lifted up. Go ahead.
Friction.
This is going to affect friction, isn't it? Friction's going to be less. So I don't know if the network's going to be greater or less. But Reese is going to tell me in a minute.
I think it will be greater.
No, I don't think you understand. You need to figure it out. I won't necessarily call on just you, but you're playing with your water bottle, and that vexes me. Seems to me like this might be well beneath your abilities. The only reason we're doing this example is because of the difficulty I had just a minute ago. You should have no difficulty doing this work. And I'm watching for the person who can't do it, because I have no trouble today being shockingly condescending. So to figure out how much work is done, let's start by figuring out the normal force. I can't get away from some of the Newton's law stuff from time to time. That's still going to be a part of what we have to do. And it seems to me that there's going to be 20 sine 30 degrees as the portion of the force that is upwards. Any surprise as where that came from? Be silent at your own peril, because if you didn't understand where that comes from and you don't speak up now, that's 100% on you. All right? There's also a normal force upwards. And there's still weight downwards. And those are the components or the forces that act in the y direction. Is this a surprise to anybody? We've done this before, right? So you figured out that the normal force has to equal 40 newtons? Because that's where we have to start. Just like the last one, the only way for us to get the frictional force is to know what the normal force is. Now, there is another way we could have done this. We could have figured out what the net force was. And we still could do it that way. But if we want to go with the plan that we started with, we'll need to know that the frictional force equals 0.1 times 40, or is 4 newtons. Any questions about where I got that number from? I'm just looking at all the people who are hastily writing things down. They should have questions, but I guess not. I'm only going to worry about the work done by the 20 Newton force and the work done by friction. Now let's see, the work done by the 20 Newton force is going to be 20 newtons times 5 times the cosine of 30 degrees. That's still true. And the work done by friction is still going to be 4 times 5 times the cosine of 180 degrees. Any questions? So as I pull on the box, I give the box 86.6 joules of energy. And at the same time, the ground takes away 20 joules of energy, leaving me with 66.6 joules of energy in the box.